Hi everyone, welcome back to homework 4. This is part 3. We're going to be implementing a flash calculation function to calculate the vapor and liquid compositions of a flash drum given a feed comprising of 10 moles of each methanol, ethanol, and water at a temperature midway between the dew and bubble temperatures and a pressure of 101,325 pascals. Okay, so we're just going to go ahead and get right in. So the idea here is we're going to have a function. So we're going to call it flash. And we're going to need temperature and pressure for this flash, which are specified. And we're also probably going to need a feed condition here. So we're going to back up a second here. Oop, the wrong way. So first, our flash pressure. That's going to be, that was just given, 101,325. And we're also going to need a flash temperature. And that's going to need to be midway between the dew point and the bubble point. So fortunately, we already kind of did the bubble point and the dew point. So we're going to have our dew temperature. That's going to be equal to nRTL dew temperature, which is actually just above here, what we did in the last video. So nRTL dew T, and this is going to be at our feed condition. So we actually probably need a feed condition. Back up again. So we're going to have our feed condition, we'll just call it NF for moles. It's going to be an array. And that array is going to be, I believe they specified 10 moles of each. So 10, 10, 10. So that's our feed. And then we're going to have this CF here. And this is going to be equal to the feed divided by the sum of the feed. So basically, this is going to be the composition of the feed. And since it's 10, 10, 10, it's going to be 1/3, 1/3, 1/3 for the feed. Okay, so this dew temperature is going to happen at the feed condition here, ZF, and the flash pressure. And then we're going to need a bubble temperature. So we'll call it bub T equals, and we already did this in the last video, so it's going to be BP at the feed condition and the flash pressure. Okay, now our flash temperature, this one is going to be midway between the two. So this is going to be, I think the way we can do this is np.mean. And then we want the dew point, or the dew temperature, and the bubble temperature. Right. Okay. Seems to be fine so far. Right. Okay, so now to actually do this flash calculation, we're going to want to supply, we're basically going to want to find a zero of a function. So we're going to have to set up a new function to actually find the zero of. We'll call it the fugacity equation. Just because Raoult's law is basically inequality of the different fugacities of the different phases. It'll take in a vector. And what we want it to output is going to be well, it's basically going to be this. We basically want it to spit out Raoult's law. So this part right here, well, let me copy it first. So this part right here is the activity coefficient that we calculated in part 1 of the homework. And then we multiply by x, which is the mole fraction of the liquid phase, multiplied by the vapor pressure at whatever specified temperature, minus total pressure times the mole fraction in the vapor phase. But of course, we need to actually specify what these are. So for that, we're going to have the moles of vapor. Now, actually, to do this, we're going to use this thing called xbit. And kind of like q to x or x to q, like what we were using before, it's basically a variable transformation. So it will transform variables between having a bounds of infinity to having a bounds of 0 and 1. So it kind of simplifies our work a little bit, makes it a little bit easier for us. So we're going to do xbit of this v that we input, and if I just scroll up here, this is where we imported xbit from scipy.special, just to show where that came from. So that's going to be our vapor phase, and then the liquid phase is going to be equal to the total, so NF, minus the liquid phase, or minus, sorry, the vapor phase. And so now our x is going to be equal to x is in the liquid phase, so it's going to be NL divided by the sum, so basically all the NLs. So NP dot sum of NL, and y is going to be equal to NV divided by NP dot sum of NV. Okay, so that's our equation there. So we basically wanted to find the 0 of this equation. We want this to set this to 0 using this information here. Now to do that, we're going to jump down here. We're going to use a root solver. So we're going to do root. And the first thing we need is a function. So our function is going to be fugacity equation. Now we also need an initial guess. So I guess going back to this xbit here, if we kind of take a look at this graph, a good initial guess will be right in the middle. So for our y values, it'll be 0 to 1, it'd be about 0.5. So at 0.5, our x values are equal to 0. So we're going to start by guessing 0, basically. So it's going to be zeros, but in an array. So np dot zeros. Zeros. Is it zeros? No, I think it's just zeros. Zeros like. It should just be 3 zeros. 3 zeros. And then that should be our. Oh, I'm getting an error here. Was it throwing me an error here? np.mean? Flash temperature equals np.mean. Maybe I'm not using np.mean correctly. I think it's just dew point, dew temperature, and bubble temperature. I'm not sure why it's doing this. We'll just say, huh. Wait, why is it? np.mean dew temperature, bubble temperature, ethanol, np.mean. It seems to be np.array. No. Unless just need some more parentheses. No, that did not work. Maybe it's not an array? No, that didn't work either. What is going on? Seems to be an issue with this np.mean. I don't know, maybe it's just some, can we just do, oops. Can we just do t minus bub t divided by t? No, it doesn't like that. Probably because it's an array. What if we look up np.mean real quick? Do we need to huh, well, now I'm confused. Well, what is bub t? Do t. Oh, I see the issue here. So our bubble temperature is a temperature. Our dew temperature is an array with a temperature. So this should be dew temperature 1. Oh, okay. There we go. I think that issue has been solved. Now I'm curious. Flash temperature. 349. Okay. That seems to be about right. So dew temperature is 351. The bubble temperature... I'm just going to restart with everything. Give it a second. Okay, we'll just take that. Where was I? Root, right. We'll call this solution equals root. Can I just do that? No, I can't. Oh, that's okay. So for the root function, the answer we're looking for is actually stored in this .x, which we've done in previous videos before. So in order to actually get the answer we're looking for out of here, we have to use we can use xbit to transform the variables. And then this will be equal to our new NV. And this is multiplied by NO. No, this should be multiplied by the total. Right, because this, yeah. Right, because these are our x's. And then we're just going to go ahead and copy this all down. Enter. And then we're just going to go ahead and return x and y. I'm going to go ahead and call flash at nf flash t flash p. Okay, and then we get the compositions. So this is the composition of x, composition of y. And I'm actually just going to go ahead and return one more thing. If we want to see how much is in the vapor phase, we can do all of the vapor, so sum of the vapor, divided by sum of the, basically, the feed. And we get about 0.64 vapor. I actually am not sure if this is correct. I'm going to go check if it's correct real quick, and I will be back in a moment. Okay, so after checking on our professor's work real quick, this is correct. This 0.642 is correct. So this is the, so after the flash calculation, this is how much, this is the fraction of vapor that's in our system. And this gives the compositions in the liquid and in the vapor phase. So yeah, that's the end of part 3 and the end of homework 4. So thank you everyone for watching, and I will see you in the next video.